Hello, my name is Frits de Mul and I would like to talk about the electric field of a thin disk. This presentation is part of a list of presentations about electromagnetism you may see here. The electric field of a thin disk. Let's imagine that we have available a thin circular disk with radius r and charge density sigma, homogeneous charge density. The question is how to calculate the electric field in arbitrary points at both sides of the disk. First we have to perform the analysis about the symmetry and so on, then find an approach to the solution and do the calculations and draw some conclusions. And we have an appendix about angular integration. First the analysis and symmetry. We have a charge distribution sigma, homogeneous, coulomb per square meter. Coordinate axes are the z-axis is the symmetry axis perpendicular to the disk. And the symmetry is cylinder symmetry around the z-axis. And therefore we better use cylinder coordinates r, z and phi. Er, the unit vector in the r direction, in the z direction and in the phi direction. How is the field built up? We have x, y, z axis and point P on the z axis. And all the Qi's at a certain Ri and phi I contribute to the electric field vector in point P. The electric field vector in point P will have components along the x or y directions and the component on the z direction. And we can expect, due to symmetry, that only the z component will be present. How to approach to the solution? Let's divide the disk in rings and segments. And we have distributed charges. That means that the contribution to the electric field in point P is given by the distributed charge element divided by 4 pi epsilon naught r squared times ER. ER is the unit vector from the charge element. R is the distance to point P. That charge element is sigma times the surface area element, and that area element is sigma times dA. A is the varying radius along the disk times A d phi, and A d phi is the length element along the tangential path. We have the z component only, and this means that the dEz is dq over 4 pi epsilon L. R squared is the scalar factor product of ER and EZ, only the component along the z direction. Again, dq ER times Ez is the cosine of alpha. Alpha is this angle here, and that is Zp over the square root of A squared plus Zp squared. Zp over square root of A squared plus Zp squared. And R is A squared is given by A squared plus Zp squared as well. Insert in the formula for the z and integrate over phi between 0 and 2 pi and r, and a between 0 and r, the radius. And when we do the integration, we end up with this expression, sigma over 2 epsilon naught times 1 minus yp over the square root of yp squared plus r squared. And now let's R go to infinity, so with an infinitely large disk, then we end up with Ez is sigma over 2 epsilon naught, independent of the radius. Go to the conclusions. For an infinite disk, is the field strength in P is given by sigma over 2 epsilon naught times the unit vector in the z direction. And since it is independent of the distance to the disk, it is a homogeneous field. Now the appendix. We have done the integration over z and a, but we also can do an angular integration. Here is the situation again, and this is the expression. dq was given by sigma dA times a d phi. And er times Ez is cosine alpha. And r is a function of alpha, is zp over cosine alpha. Zp over cosine of alpha. Alpha is this angle here. And a is zp times alpha. A zp times alpha. This means that dA is zp over cosine squared alpha d alpha. Insert, then we have this expression here. This is A zp times alpha times zp over cosine square alpha d alpha, that's dA times d phi cosines alpha over 4 pi epsilon naught zp squared cosines minus 2 alpha. And here is the expression again. And this can be simplified to set the integral over r 2 pi sigma sine alpha d alpha over 4 pi epsilon naught. And when you integrate, it ends up in this situation, this formula here, alpha max minus cosine 0, and when alpha max is pi over 2, we end up with this expression. It's the same expression as we had before. And for r going to infinity, for an infinitely large disk, the field strength in P is given by sigma over 2 epsilon naught, a homogeneous field. Thank you very much.